Hi, today we are going to present our project Thermodynamic 2 and our topic is Refrigeration Cycle. Our journal title is Experimental Performance Assessment of a Hermetic Reciprocating Compressor Operating in a Household Refrigerator under on-off cycling conditions.
I am Chong Jin Ro.
I am Ko Hui Yu.
I am Chang Su Hui.
Hello, my name is Abdullah Jamal Ahmed Johan Bamatraf.
I am Ting Hui Kian.
Introduction. Refrigerators are very fundamental in the everyday life of our society. The performance of refrigeration system mainly depends on the hermetic compressor. This paper presents a review of most critical parameters and their influence on the hermetic reciprocating compressor performance. The overall performance of refrigeration cycle is not only dependent on the efficiency of its components, but also on the way these components interact with each other. The basic principle of the system. The refrigerant cycle is approximately a Rankine cycle run in reverse. A working fluid, often called a refrigerant, is pushed through the system and undergoes a state change from liquid to gas in reverse. The latent heat of vaporization of the refrigerant is used to transfer large amount of heat energy, and changes in pressure are used to control when the refrigerant expels or absorbs heat energy. However, for a refrigeration cycle that has a hot reservoir at around room temperature or a bit higher, and a cold reservoir that is desired to be around 34 degrees Fahrenheit, the boiling point of the refrigerant needs to be fairly low. Thus, various fluids have been identified as practical refrigerant. The most common include ammonia, freon, and other chlorofluorocarbon refrigerant (CFC), and HFC 134A, a non-toxic hydrofluorocarbon.
The next one is schematic drawing and the explanation. This is the schematic drawing that set up from our experiment. The tests were conducted with a refrigerator equipped with a hermetic reciprocating compressor and a natural draft wire and tube condenser. The compressor is the main component of the refrigeration cycle, as electrical power is required to supply the required mass flow rate of refrigerant for the system and establish the pressure difference between the evaporator and condenser. The air temperature in the freezer and in the fresh food compartment was controlled by a thermostat. Besides that, this study measured the refrigerant pressure and temperature in the compressor inlet and outlet, and compressor shaft temperature and power consumption. A simulation model was developed to predict mass flow rate, power consumption, and compressor temperature, showing good agreement with experimental data.
These two pictures are the example of the hermetic reciprocating compressor.
Method of performance analysis. Graph A and B shows the PV diagram after compression startup and before shutdown for condition 16B, while C and D is for condition 32B. It can be observed that the indicated power is higher during the compressor startup, which is directly related to the higher mass flow rate brought about the lower pressure ratio, which then increased during the remainder of the on period. Higher mass flow rates also induce higher power losses in the section and discharge processes, as can be seen by the significant area above the dashed line in graph A and C. From graph B and D, one can clearly see strong pressure oscillation during the discharge process, suggesting rebounding of the discharge wave. Next is ideal vapor compression refrigeration cycle for process and analysis. Process 1 to 2 is isentropic compression with formula work equal to H2 minus H1. Process 2 to 3 is constant pressure heat rejection with formula heat transfer QH equal to H2 minus H3. Process 3 to 4 is cooling in expansion device with formula H3 equal to H4. Process 4 to 1 is constant pressure heat absorption with formula heat transfer QL equal to H1 minus H4. And below shows the analysis for steady flow device and performance.
Now I will explain about the performance calculation of the system. All the temperature are assumed because the journal is not giving the data of temperature, and all the data that I got are referring to the thermodynamic table of saturated R1348. Assume phase 1 is superheated vapor, P1 equal 1 bar equal 0.1 megapascal. T1 larger than saturated temperature at 0.1 megapascal equal negative 26.43 degrees Celsius. Assume T1 equal negative 10 degrees Celsius, then I will get H1 and S1. Assume phase 2 is compressed liquid, P2 equal 4.4 bar equal 0.44 megapascal. T2 smaller than saturated temperature at 0.44 megapascal equal 11.65 degrees Celsius. So I assume T2 equal 52 degrees Celsius. So I will get H2 and S2. The step calculation is repeated same as phase 2 for phase 3 because phase 3 is compressed liquid also to find H3 and S3. Assume phase 4 is saturated mixture, P4 equal 0.8 bar equal 0.08 megapascal. In this condition, H3 equal H4 equal 88.61 kJ per kg. In this condition, we should find quantity X to get S4 by substituting the X in the saturated mixture equation. QL equal mass flow rate times H1 minus H4. By substituting the data, we will get 296.571 kJ per hour. For W in equal mass flow rate times H2 minus H1, so we will get negative 228.228 kJ per hour, negative mean work done by the system. And the last one, we can calculate the COP equal QL divided by W in equal 1.299. The calculation that I explained in previous slide is for condition 16b after startup. The same calculation are repeated for condition 16b before shutdown and condition 32b after startup and before shutdown.
Now I want to discuss about the suggestion of system improvements. To improve the efficiency of refrigerator, we need to reduce the losses in evaporator, condenser, and compressors. So now we look at the factors which reduces the losses in evaporator, condenser, and compressors. First, we need to reduce the evaporator losses. Evaporator losses can be increased by the evaporator pressure or temperature. A high evaporation pressure or temperature indicates the system is drawing heat from the product without expending too much energy. Hence, we need to size the evaporator correctly. Size the evaporator to suit the load. A small evaporator may have a low capital cost but may require a larger compressor to cope with the load and so have higher operating costs. Second, we need to reduce the condenser losses. In order to do that, we need to clean the condenser. Keeping the condenser clean and in good condition, for example, no block or corroded, promote efficient energy transfer. Last, we need to reduce the compressor losses. Compressor or the refrigerator system consumes work added to 100% of the total energy used. So, compressor selection is important. The efficiency of the system is measured by the coefficient of performance. This is the ratio of cooling output compared with the energy input. Thus, the higher the COP, the more efficient the system. By considering all losses, we reduce the effect, which result refrigerating effects are increases, thus COP increases.